All right, welcome back, everybody. We're in week 3. So just a reminder that most people submitted homework 1, which is mostly the review stuff. You should have already gotten your grade. Again, we're doing completion-based. And a few people that didn't submit it, I emailed you, and week 3 is the drop add deadline. Think about dropping. So I'll leave it at that. But is anyone here still on the wait list? There are only 3 people on it. They didn't submit it. They're not here. Wait list is closed. So, okay. Now, let's see. Last time we were talking about the devices, transistor devices. We spent a lot of time talking about operation, how to figure out this like R-on resistance. Remember, the resistance is actually kind of changing over the operating voltage of the transistor as the output transitions. But we can approximate it as this first order resistive model, right? And I need to finish up a couple slides on this lecture, and then we're going to talk about delay of gates. But we also looked at the layout a little bit, and I'm going to have another lecture on Thursday that's all about standard cell design and other caveats about this. So your homework 2 is going to involve using K-layout, looking at layouts, things like that. That's due on Sunday, so there's less of a turnaround this time. Don't wait until the weekend. I encourage you to start the homework early. Try it. Again, it's still completion-based, where we want to see a good effort. And we already released the solutions to the first homework. So if there's questions or you want any help with that, let us know. So one important thing, though, is you're going to get better at recognizing layout. I've mentioned I've changed the learning outcomes of this class over the years, where you used to spend a lot of time creating layout, but really one of the learning outcomes I want to have is I want you to be able to read layout and understand what's going on. It can be kind of hard from an image like this. It's a lot of colors overlapping. That's why homework 2, you use the K-layout viewer, you dig into it, and you can kind of turn on and off layers, see what overlaps. There's this interactive process, right? You can even do that like 3D view. Most tools I mentioned in industry don't have a 3D view like that. So that's something that you could do it in this class, but you won't have access to in industry. But after that, you're going to start to recognize kind of patterns and things. And just the most important thing I would say is looking at how diffusion merging of adjacent transistors, like you can see, wrong color. You can see in this area right here, we have a polygate here and a polygate here. And those are connected in that area I circled through the green diffusion layer. But then they go up through that Li contact into the Li layer. So recognizing that level of that connection method is important. When you have complex gates, you try to make as many connections as possible through the green diffusion by just placing transistors next to each other that they connect to. Whereas if you look at this, you can see over here on the kind of this side right here, you can see a break in that diffusion kind of up here, right here, but you don't see one down in the bottom. And so what the reason for that is that this right here is ground, and this right here is VDD, and this is probably going to be an inverter. And so you start to see these patterns in the things you look at. You'll frequently see that on the output as well. Look over here, you can see kind of a break in the diffusion right here. And this one is also ground. And so this over here is also probably an inverter. And you can start to recognize these topological structures. Now, if you search for this, the Sky 130, this gate, you'll find a data page online. It'll show you that as the schematic of this inverter. That is not the transistor level schematic. That is a logical schematic. So when I ask you in the homework, what is the schematic of one of these gates, don't look it up and just copy that. I want transistor level schematic, where an inverter is going to be this, right? Not this, just to be clear. So you're going to get some practice with this. There's hundreds of gates in the library. You can go into them and you can see what the layouts are and you can kind of look at them. Now, besides resistance, there's another important part to delay. On homework 1, you had to do this capacitor discharging, right? That's the model we're going to start to talk about with gate delay. But first, we need to know, what are the capacitors? We have the resistive part, that's the gate charging or discharging a capacitance. The capacitance is going to come from the layout itself. And that's why understanding the layout also helps you understand what causes capacitance and how to minimize it. So simplest model of a capacitor, and this again should be review, is a parallel plate model. You may not have heard it called a parallel plate model, that's fine. But it looks like something on the right here, where you have basically two conductive plates separated by an insulator, and then you have electric field between those plates. It's not only directly between the plates, but you also have fringing, like on the side here. So that's a fringe capacitance, where it's on the fringes or the borders of the parallel plate. And this is basically the first order way of modeling a capacitance. And we're gonna look at the different layers that can form these parallel plates and what the capacitances are. Now, when you have this, just like when we talked about resistance, we had the W of a transistor, the L of a transistor, and we could translate those into the R on of a transistor. We can also have the W and L or width and length of different shapes, so not necessarily of a transistor, that can create an area like this. So this is a different W and L. So let me call it, I don't know, let me call this H. No, I'll call that W2 also, but I'll call it like W1. And I'll call this, W2. So this is the shape, it's a square that forms these two parallel plates. And the area of that is equal to the dimensions of the W1 times W2, right? Simple geometry. So this is the top plate and the bottom plate, and it's separated by a dielectric that is distance d apart. So again, this is going to be silicon dioxide typically. And this forms a capacitance with the formula down here that's dependent on those three parameters. 1, the distance d, the separation of the plates. A is the area. And then this, which is the permittivity of the dielectric. It's a constant. Okay? And that gives you your capacitance. Now, where do these occur? Well, they occur in many different places when we manufacture these different layers, right? Because if you have two parallel plates, we're doing, device layers, poly layers, metal layers. There's capacitors everywhere in this entire stack. Some of them are more significant than others. And so we tend to look at a few of them as the most significant. And if we look at, for example, a transistor, we have, again, the length going horizontal here, and we have the width going vertical here. We talked about this layout, and we see the side view of it. There's a few different capacitances that contribute to the gate of this transistor. And so what do I mean by the gate? Again, if we have an NMOS, this is the G terminal. This is basically going to be a capacitor right here called CG on the input of that gate. Now, what contributes to this? Well, there's two components that are the most significant part. One is this CG term right here, which is, again, just following that exact formula I mentioned. We see the width and length of the transistor here, which is roughly the area A, and Tox here, which is the same as D in that previous diagram. Because again, we have a polysilicon over the silicon, the substrate, and they're separated by that gate oxide that you control the transistor through. So that basically forms, and then the permittivity right here of oxide. So this formula right here in the bottom is this exact same formula I showed right here. Permittivity times A over D. Except A is the width and length of the transistor, D is the thickness of the oxide. Yeah, so you can see on the right, I just kind of show that equivalence. So this is one of the most significant parts of the gate capacitance. There's actually another component of this, and actually, do I have it on the next slide? No, I don't. So I'm going to actually put that right here. there's actually one more component here that is sometimes considered, which is this one depends on the whole area. There's actually another one that is the overlap right here. And that's frequently also determined by, it's called C overlap, OV. And as we see, when we did the diffusion of the source and drain of a transistor, it gets heated up, and you know that these source and drains they can go in all directions when they heat up due to the diffusion process. Some of them means it goes underneath the gate a little bit as well. And so it's this kind of undercutting. And it can do that by this dimension, XD. You can see it in the diagram here, if I change colors, XD. Let me draw this whole thing in a different color. And so there's another dimension there, XD. And so the overlap capacitance can actually be a different value of this gate capacitance, which is frequently the area XD times W over, again, Tox here. And this is another component of it. And this is just due to those sides of the transistor. And you can see as you scale wider transistors, that scales more. Why is it different than this C gate? Well, it's a good question, but because sometimes your channel, when your transistor is off, you don't have a channel here, and so that you don't have a capacitance between the gate, the poly gate, and this channel. You just have a capacitance between the poly gate and the poly gate and this. So when it's off, you're essentially got two little capacitors here and here, whereas if you have a channel forming, you have a capacitor of this whole thing. So that's a case of actually the operating mode of this transistor changes what this C gate is. But for the most part, we're going to assume some simplification of either one of these. Either it's off in the top case, or it's on in the bottom case. Does that make sense? It's basically, what is the capacitor? It's either between, the parallel plate is either from here to this whole channel under here for the red, or it's these two little capacitors here and here for the blue. Okay? But it's just a parallel plate, right? Two conductors sandwiched by an oxide, and the dimensions depend on the layout. But this overlap component is not something you drew as layout. That's something you know that happens during the manufacturing process, and they have to tell you what XD is. Because that's not the interaction of any shapes that you drew. It's when they implanted the source or drain, depending on the implantation and the temperature of the steps after that, it undercuts by some amount. That'll be in a SPICE model, for example. So you can do circuit simulations. The fab will tell you what that is. The fab will also tell you what is the thickness of your oxide. What is the permittivity of your oxide? These are all parameters in what's called the device model of a transistor. W and L are something you know because you drew those shapes. Those are design parameters. Now, that's the gate component. There's also source and drain components. So if I draw a transistor again, like this, I previously talked about the gate terminal. Well, I also have a capacitance that could be here. Call this CD for drain. And I could also have a capacitance here called CS for the source. Now, these are the diffusion areas that are the source and drain of the capacitor, of the transistor itself. And you can kind of view these as basically a 3D model again, where the source or drain is, when we drew it, you drew the poly gate like this, and you had your diffusion over this thing. Basically, this corresponds to this 3D view, right? Kind of this right here corresponds to this whole thing over here, this source area. And you can see it goes down into the substrate, right? Now, you can view this as basically a 3D structure where it has a bottom, and there's a bottom to the substrate connection. Let me step back. When we have this, what is this formed with? This is either going to be P-type here and N-type here, or N-type here and P-type here. right? We talk about diodes. So this material, this source or drain with the substrate forms a diode. And remember, we have this diffusion region between the terminals of the diode. And so anywhere that this structure has this NP shape forms this diffusion region, which that itself is a parallel plate capacitor. The diffusion region between the P and the N is the insulator between the parallel plates, and the P and the N are the parallel plates. So what we can see here is effectively we have 4 capacitors here. One is going to essentially be this sidewall like this, or this sidewall. Another one is going to be, say, this sidewall. Another one is going to be this sidewall. And then you're going to have one that's basically the bottom of this region. Okay? So it's kind of like a 3D structure, right? If you view this thing as kind of we just looked at, this side, the back side, and then the bottom of this kind of rectangular shape. Now, why didn't we look at the top? Well, the top is going to have some contacts, but then a thicker oxide. And so generally that top won't matter because that oxide on top is going to be quite thick. So it's not significant, really. This diffusion region, though, between the P and the N is very thin. And so according to the capacitance equation, if you have a very thin, small d, that means the capacitance is big. So this thin diffusion region can be significant. So what do? Well, we just add up the different areas of these things. So this diffusion capacitance is the bottom capacitor plus the sidewall capacitors, one here, one up there, and this other side. Now, the dimensions of these can be calculated from basically this, except for the depth of this thing, right? How far down? That has to be a parameter you're given. But you know that the sidewall is going to be the distance of basically this perimeter here. That's how far around you go to have a capacitor from here, here, and here. And then the bottom area is going to be the area of this because it's between this and the substrate below it. And so you can formulate those all mostly in terms of W and L, but then also this junction depth parameter, xj, which is, again, another SPICE device parameter that they'll give you. And so you then just need to figure out the area of the bottom times, they give you a parameter that's going to be the capacitance of the junction. This is, again, a SPICE model parameter. And then you can also have the perimeter, and this constant is the capacitance of the sidewall junction. The perimeter times this gives you a capacitance. These are in your SPICE model. And then you're going to have basically this right here is LS times W is the area of the bottom part. This 2LS plus W is the perimeter of the thing around it. So that's the perimeter, excluding the channel side. Again, that's excluded because sometimes it's on, sometimes it's off, and so that changes the behavior. This together forms the capacitance of that region. Now, why do I show you all this stuff? All these parameters are actually in the SPICE. If you get down to doing analog design, they do ballpark hand computations of this stuff. But it also helps you understand, why do I care about having small layout? Well, I want to make this area as small as I can because making it bigger increases the capacitance. Making it bigger makes it slower. And so you want to make this as small as you possibly can. Now, I'm going to generally have a... now, there is a little bit of resistance also associated with these besides the device resistance, which generally this is ignored for the most part in digital, where if you have a contact to a source or drain, there is some sort of resistance going through this diffusion material too. It's usually not that significant for digital stuff, but it's there. And that depends on the area of this. We'll talk about this type of modeling a little bit more when we talk about interconnect, where it's more significant. But I just put this here for reference, that there is some resistance, and this is not the R-on of the devices. of the TX transistor. Now, one thing you frequently do in layout, and this is a technique to decrease capacitance. Let's say I want to make a big transistor. Well, if I do that, let's say I want to make it double the width. What happens with the resistance when I make it double the width? It has half the resistance, right? The resistance goes down by half because I made it twice as wide. More electric current can flow through this transistor. That's great. But now what happens to the capacitance? Well, I doubled that bottom area, so that component's double. And I didn't quite double the perimeter. I doubled the vertical part of the perimeter, but not, this dimension here. So the perimeter almost doubles. That's bad. If you make a big transistor and you keep making it taller, you have the resistance, you double the capacitance, what we're going to find delay is going to be proportional to RC. It doesn't get any faster. So what you want to do is you want to do tricks where you can improve the layout. This is an extreme case, where instead of doing the thing on the left, you do the thing on the right, which is called folding a transistor. So instead of having one really wide transistor, you have two transistors in parallel, but they're both of length W. And then if you notice what I did here, I shared this area. Remember, we showed diffusion sharing to minimize the size of the gate. It's not only to minimize the area, but it's to minimize the capacitance here. Because now, if you look at this, usually you don't care about the capacitance to ground or VDD. They're big capacitors. They have a lot of stuff connected to them. So these capacitances here, I don't care about. What I care about is that middle one. And what happened is, well, what is the area of this? Well, now it's just W times whatever this is, L. Actually, the area is that for the CJ part, the bottom wall, right? Now, what is the term for the perimeter part? Well, remember, we ignored the perimeter part that's connected to the actual channel of the transistor. So in that case, we can kind of ignore that component going to the left and right because both of those are transistors. So the only part I have of the sidewall capacitance is the top and bottom of that center area. Right? It's just this part here and this part down here. So I've effectively reduced that capacitance. Well, W is the same, but then I instead of doubling the sidewall capacitance roughly, I actually decreased it. Because, in this one on the left, I didn't include this side of the perimeter because it's the channel side. And on this one, I didn't include either side because they're both channel sides for different transistors. So basically, you can decrease that area, have less sidewall capacitance, and it makes a faster transistor. So this is by not making it larger, but then also saving capacitance. So then this is the area part. And then the sidewall part, well, let's call that LS still would be just C junction sidewall times C times LS times 2. So if this term between these gates is LS, it's only that term. Whereas in the previous slide here, the perimeter included this component, W, which we don't have that now because we have channels on both sides. Now, I'm not going to go through an ngSpice demo right now, but what I would generally do is go in and actually show you the models parameters in ngSpice. And I'm going to do this next lecture because I'm going to also run some simulations. When you go into the ngSpice models that you download from the tutorial, you can actually find parameters like CJ, CJSW. You can find VTH. You can find XD. All these things are actually in the SPICE model. These are old SPICE models. If you look at newer SPICE models, the level of the model ends up going up, and you have more complex ways of modeling it. But these are kind of the old standard models which give you insight into how the layout affects the performance. Okay, so I'm gonna skip this for now. Now, what we want to do though is start to look at how this affects delay and power. Oop. So we're going to talk a little bit about switch transistor networks, and we're going to talk about first order gate delay model, or Elmore delay. This is one of the most important learning outcomes of this class. Elmore delay is a good first order delay model that gives you intuition into why things perform the way they do. As a digital designer, it's better than just a switch model with no resistance because you include resistance and capacitance, but the equations and stuff are very simple. You can do things with little calculations. You don't need SPICE. But more importantly, you can get intuition into why things behave the way they do. We're going to use this for devices, for gates, and we're also going to use this for interconnect and wires. I'm going to have entire lectures on how to model wires and understanding that. And then it also gives you a little bit of intuition into power consumption. I'll talk just a couple slides on that. So again, we have this R on resistance. We talked about it last time. It's over the average of the range of operation of the transistor, right? When it's in the saturation mode and the drain is at VDD, it's going to have this bottom resistance here, R0. And when it halfway discharges, it's going to have this resistance here. The slope of this is the resistance halfway discharged. We average those to come up with the R on, which is the average over the operational range. Below that, the current starts going down. The transistor's basically discharged everything, and it starts to kind of shut off, essentially. So we're assuming R on. Now, the other thing to remember is we talked about W and L with the current equations. When we talked about those current equations, we basically said ID, which is the current of a transistor, is proportional to, it was a bunch of stuff, but it was W over L. Now, another way to translate that then is to voltage. If we have voltage, we need to know the resistance. And so we're going to instead use this idea of if you have a current going through a resistor, Ohm's law, basically, if the current increases, if the width increases, the current increases. If the length increases, the current decreases. The resistance is the inverse of current, right? That's just Ohm's law. So if you say V equals IR, another way to say that is, I equals V over R, or I is proportional to 1 over R, right? Just different relationship. So if we increase the length, the resistance goes up. If we increase the W, the resistance goes down. Same equation, different view. So we also want to then think about if the resistance goes up in the length of the transistor, that's like you're having more resistors in series because the channel's longer. And so effectively the resistance goes up. If you make the transistor wider, that's basically you have more resistors in parallel, and you know that parallel resistors mean the resistance goes down, right? We just did the question on the review homework, parallel series combinations of resistor networks. And so we can then get to this equation. Now, we want to then look at delay of these transistors. So if we look at this is basically an inverter, and if we have the ratio of the P and the N. So remember, this is equivalent to essentially a resistor network with a pull up through the PMOS resistor and a pull down through the NMOS resistor. But remember, only one of these is going to be on at a time because the inputs have, the PMOS has an opposite polarity, right? So when I draw it like that, I'm not saying both transistors are on. I'm just showing it as, you could add in the switch model to be explicit, right? If I were to say, have a switch in here, and maybe a switch up here. But if you look at this, the sizing of these, remember, we can choose the width of the transistors. We were talking about the balance of the rising delay pulling up through the PMOS and the falling delay or pulling down through the NMOS. And you can basically see those in this diagram. So here is the low to high transition. So that's the delay it takes for the PMOS to pull the output up from 0. And over here is TPHL. This is the high to low transition time. That's the time it takes for a transistor to pull the output from VDD down to ground through the NMOS. And over here, we can see this is the width ratio of the transistor. So the PMOS width compared to the NMOS width. Remember, I told you PMOS devices are bad transistors compared to NMOS. So we always want to increase that PMOS size in order to balance the delays. Well, that balance point is right here. This is where the high to low time matches the low to high time at about 2.5x. That, again, was the ratio of the mobilities of the carriers, so the mu p and the mu n in those device equations. Now, once we start to factor in other secondary effects, though, we can look at TP. This is basically either the average or the maximum delay of the inverter, depending on how you interpret it. And that minimum of the delay is also roughly about equal to that. So again, about 2.5, depends on if you make them perfectly equal or the maximum. This one can include those secondary capacitive effects of the source and drain and the gate and so on. Now, this ratio of these sizes of the P to the N has a special term, we call it beta. It's the beta ratio of a gate, which is the P to N ratio, or the sizes of the P pull up to the N pull down, to roughly give them the same delays. You'll have different libraries that are designed in different ways, but usually this is fixed for a given set of cells. Now, what we're going to also do is we're going to talk about relative resistances. As a digital designer, you don't typically talk about the actual resistance of an inverter. What you will talk about is you'll say, oh, if I have a width that's twice the width, that's going to have half the resistance. You just know doubling the width halves the resistance. If you have 4 times the width, you have 1/4 of the resistance, that ratio. You also know that the device types change the resistance. If you have a PMOS of the same size as an NMOS, it has twice the resistance, roughly, 2.5 times the resistance. Depends on what I tell you that beta ratio is. Or if you have a PMOS of size 2W, it has the same resistance as an NMOS of size W, right? So 2 components, the size, W, and then the device type together determine what the resistance is of a transistor. And we're going to typically talk about basically R unit. This is usually kind of the resistance of the smallest NMOS. And the nice thing here is you can just say, oh, R unit or R inverter or whatever is the smallest resistance. It applies to any technology. So you don't have to know that, oh, this is 5 kiloohms or something, because that can change with every technology, but there will be a fixed resistance for a smallest inverter in a given technology. And then you can scale everything from that. Now, again, when we have the inverter model, we can now have, during pull down, we're discharging through Rn. In this case, the input is logical 1, so this will be VDD, and it will pull the output down to ground. In the pull-up case, the NMOS is going to be off, the PMOS is going to be on, we're going to have RP, and that'll determine the resistance of this device. Now, there's a couple important things to note are the noise margins. In all CMOS gates, the output low voltage is 0 volts. In this left case, this resistor will fully discharge this output until this becomes 0. Otherwise, you have current going through this due to Ohm's law. Right? If the voltage here is different than ground, it's going to discharge it until this is 0 volts. Similarly, over here, this is going to charge this up to VDD. When VDD happens, the voltage across that resistor is 0 and then you have zero current. So you know that the output high voltage is VDD, the output low voltage is V output low. This is guaranteed for all CMOS logic. And then VM is going to be what's called, this is going to be the, sometimes it's called the switching point of the inverter. There can actually be a case where you don't immediately turn the PMOS on, off and the NMOS off. There's a brief time in the middle where both of them are actually on a little bit. And this VM is essentially that midpoint voltage of when this transition of one off to on happens. So that's the midpoint or the switching point of the inverter. Now, you may ask, why did I give you that capacitor equation in class, or in the homework? Remember, out here, you're going to have a capacitor. Out here, you're going to have a capacitor of driving the fan out. The delay of this is actually going to be identical to a capacitor discharging. And we'll talk more in a few slides. And you can see that behavior, though, where if you have a step input, you end up, so on the top here you have basically an input that's not a step input, but it's not an ideal staircase waveform, because in real circuits, nothing is perfectly square like you saw in 100 or 125. Instead, an input switching is going to look something like this here, which is, this is this is T rise of the input, and this is T fall of the input, because you can see it's the time that it's going to go up or down. And there's kind of this sloping where, if you look at this sloping, the edges are curved, kind of rounded, because you're charging and discharging capacitors. So that's that first order filter effect of an RC system. And this is from the input, and you can see going to the output, if you have an inverter in this case, so V in and V out, you're going to have an input that starts transitioning at a certain time here. We're going to measure all of the times of transitions, of delays from the 50% point of a signal. So this is 50% of VDD. Now, why do we do that? Well, because it's kind of all over. It's a range from 0 to VDD. At which point do we define the transition? Just pick the middle one, the kind of the middle and the horizontal voltage sense. And that's the signal switching. Similarly, there's another 50% of VDD when the waveform falls over here on the right. This is also 50% of VDD, but just in the other direction. So there's a signal switching. Now, when we measured the delay, we want to then measure the high to low delay. So you can see this first input is rising, and then the output falls. When we measure the delay through the inverter, it's from the input rising to the output falling. So 50% to 50%, that's the definition of the high to low transition. Similarly, when the input falls and the output rises, we have a 50% to 50% to get the low to high propagation delay. So this is for delays. 50% always for delays. Now, there's another component here which is typically called slew, or slew rate, where it's not really a rate, it's usually a time, or it's often called rise fall time to be most accurate. These are really all the same term, but you'll hear me say them kind of interchangeably. And what this means is this is kind of a description of how not digital is my waveform. Right? If I look at this output falling, this is the falling transition time. You can see, and we're going to measure that actually not from 50% though. This is going to typically be measured from 90% to 10% and 10% to 90%. Question?
Why specifically 10 and 90? Is it because of noise?
The question is why 10 and 90? Well, this is kind of asymptotic, right? And this gives you kind of an idea of that linear, it's mostly linear between that point. It's not always 10 to 90. Okay. I actually think in Skywater it's 20 to 80, I believe. I forget, but I'm pretty sure it's 20 to 80 in Skywater. Mm-hmm. It changes. It's usually when they have it for a given library or technology, they'll fix it though. And every signal is in terms of that. Yeah, and so this over here is, this is also 90% here to 10% down here. Now, why do you have to model that? Well, those slews actually affect the delay too. Because if we go back to this case, what happens when V in is 50% on an inverter? Let's say I don't have an inverter, but this switch model assumes the left one, the input's VDD, the output, the second one, the input's 0. What happens when input's 0.5? Well, that's roughly this VM where it's both transistors are kind of on, but they're switching off. And so you end up having two resistors temporarily having current go through them. Just for a brief amount of time, till the input finishes transitioning, then those transistors will go into one of these two states. But that has impacts on your power consumption, we'll find out. And it also has impacts on kind of the slew rate or the rise-fall time of your output signal. Generally, if you have a slower transitioning input signal, your output's going to also be slower. Or you could have a case where you have an inverter and it's driving a really big capacitance. In that case, you're going to have something like this, but then this is going to be like a big tail here. It's going to take a long time to discharge this because that inverter is really small and there's a big capacitor. And if you do that, it basically shifts this because you have those long capacitively dominated discharge times, right? So you can have two components that are going to end up affecting the performance of your circuit. Yeah?
What does the P stand for?
P is, good question. P in this case is propagation. Yeah, these terms and kind of notations differ from every textbook and so on. I'll generally use the term, the colloquial terms when I use it, not require you to memorize particular notations. Now, I often find people mix up when to use 50% and when to use 90 to 10, but it's important to remember the delays of signals propagating are for 50% and slews or transition times are the 90 to 10. Question back there. Yeah, well, you can see, actually this is TF for falling transition. This is TR for rising transition. Then this is TPHL, TPLH. So this is from the input rising high to the output going low.
Then like the TR, like the top or the
Oh, because that one will be measured. I should draw it completely. That would be measured from here to here. Let me say TR. Just to be clear that an input can also have a transition time. Yeah. I should be clear about that. So the inputs have transitions as well as the outputs, and they're not equal. They can be different. Questions so far? Again, this is, yeah, back here.
You said it's maybe different from inputs outputs with the transition time. Is it generally going to just get worse, like the transition times are going to get longer as you go from more input, like further down the line?
It's a good question. The question is generally, I'll summarize it for the mic. And so if you have multiple stages, what happens to these? Does the transition time generally get worse as you move down the stages? The answer is no. Because I gave you kind of two cases where you'll end up having a big output transition. One is going to be if you have a really slow input transition. Or another case is if you have a really big capacitance on the output. Well, when you have a bunch of stages, let's say you have a slow transition going to a smaller inverter with a small output capacitance. That little inverter could catch up. And basically, it can drive its output very quickly. And it will basically make a slow input transition become a sharper output transition. And after a couple stages, you could restore the slew. We'll find later, I'll talk about buffering for logic signals. Frequently we do buffering to address exactly that, to improve the delay of interconnect, but also to improve slew rates of signals. Yeah, we'll talk about buffering later in the quarter, after the first midterm. Now, so we have this idea of this discharge. Let's kind of go up a level and start talking about logic gates. So now, again, we have CMOS gates. There's a parallel series network of NMOS, parallel series network of PMOS. I'm just going to show NMOS in this example, but think about these two cases. If I have, for example, a NOR gate, the NMOS of the NOR gate on the left, or the NMOS of a NAND gate on the right. NAND has the two series pull downs, and both of the inputs have to be 1 to have an output of 0. The NOR gate here, you have two parallel transistors, and the output will be 0 when either one is on. And so the case here is series, I always have half the current. And another way to think about it is I always have double the resistance when I have those two series transistors, right? R on of that NMOS and R on of that PMOS, add them up. If it's pulling down, that's my resistance. The one over here, if I have a NOR, there's actually different combinations of inputs that might have both of the transistors on, or it might have one of the transistors on. If both of them are on, I have two parallel resistances, and my resistance is obviously the inverse of resistance is some of the conductances, right? Here's conductance of 1 over R, conductance of the other equals the conductance of the whole thing, 1 over R. But that's only if both of them are on. What if one of them is on? So let's say this is off. Well, the resistance of this is RB. The resistance of this is actually faster than the resistance of that in that case. Or I could have the case where only that one's on, and it's be RA. Yes?
In this case, how would you size the pull-up network? Because you've done different times.
I'll talk about this coming up, how we do the pull-up networks. We're going to exactly go to that question. So this one has sometimes double the current, depending on the logic inputs. And that's the thing to think about. A lot of times when we talk about gates and the delay of gates, you want to think about the worst case delay. So sometimes you might want to care about the fast case delay. We'll talk about this all during static timing, but for this case, if we want to find the worst case delay of this gate, we have to assume that one of these PMOSs or NMOS is off, and we're pulling down through one of them at a time. Now that we can do that, basically any CMOS network can be converted to an equivalent R-on resistance. Do the series parallel combinations, assume anything in parallel, that the highest resistance is the one in your path, because you don't want to do both of them because they might not be on. So you want the slowest path generally. You figure out and you come up with the resistance of your pull-down network. So that's why we had examples in homework 1 of doing that reduction. This could be a single transistor if it's an inverter. Or this could be the pull-down stack of a NAND gate. Whatever it is. We end up having this delay. The high to low is going to equal this, and this is the magic constant for the Elmore delay, 0.69. And then it's RC. Now, what is this from? This is from the problem we had in homework 1 of the discharging of a capacitor. If you have a step input and say at time 0, the switch opens, and we're going to start discharging through this, that step opening is called an impulse, and then this is the response of that RC network discharging. It's also the low-pass filter, the first-order low-pass filter. And it's going to be 0.69 R on times C. Now, in the homework, I gave you the derivation of this. If you don't remember this, I always remember 0.69. It comes from a logarithm, where if we want to write out the equation, we basically, again, want to measure the delay to what point. When we talked about definitions of delays, we measure delay to the 50% point, right? So what do we want here? Well, we want 50% of VDD is going to be this point kind of right here. And we want that to equal VDD times that exponential decay function that we had in our homework. This is the discharging of a capacitor, negative T over RC. This RC is R on times CL in this case. Well, how can we then solve this? Well, let's just do the math. You can say, okay, if I divide both sides by V to D, I end up with 0.5 equals e to the minus T over RC. How do I get rid of the exponent? Well, I can do the natural log of both sides. Natural log of 0.5 equals minus T over RC. And then I end up with the log of that number is a negative, so then that actually ends up being 0.69. And so if I kind of multiply by RC in the negative, I end up with negative natural log of 0.5 RC equals T. And in this case, TPHL. That's where that negative log, so it actually should be negative log of 0.5. That gives me the 0.69 RC. Now, what if I wanted to measure the slew rate of this, for example? I could do that too. How would I measure the delay, say, from 90%? Or what if I measure the delay to 90%? Well, just substitute 90% here, right? What if I want to measure the delay to 10%? Put 10% here. Subtract the 2. Then I have my slew of this. So you can use Elmore also to approximate the slew rate as well. But the one that we usually remember is that 0.69 because that's the 50% delay of this equation. And again, this solution's in the homework too, in that question, homework 1. Yeah.
The R on and CL come from like transistor itself, right?
Yeah.
They're not added.
So where do these R on and CL? Yeah, zoom back up to the big picture. This is the transistor network itself. So if it's an inverter, it could be one NMOS, or it could be, if we have a NAND gate, it could be the pull down through both the pull downs in the NAND gate. You know, 2 transistors in this case. If they're sized the same, it's just double the R of the NMOS. If it's a NOR gate, like over here, if both of them are on, it would be these in parallel. But if only one of them's on, it's one of those pull downs. So it kind of depends on the inputs. Now, what about the CL? Well, if we go all the way back to it was the previous slides, but remember we have CL is going to be the fan out. So it's going to be, this inverter is going to be driving, say, other inverters, a flip-flop, a wire. All of those capacitances are going to add up and basically present a load capacitance to this inverter. And so that is this driving that output load capacitance. Yeah.
If we're calculating this 50% delay like this way, and we also calculate the slew rates using 0.1 and 0.2, does that mean that basically the slew rate is usually going to be proportional to this delay?
Yeah, that's a good question. So if we do that, what is the slew rate proportional to? Well, it's, was it natural log of 0.9 minus natural log of 0.1, I think, times RC. I think it's basically that. Yeah. The problem is that's actually a bad approximation because how linear is that? By definition, it's an exponential decay. And so it's not a linear model of an exponential decay is bad, a bad model. So this is proportional to the slew. All right. Any questions so far? So now we mentioned the question here. So what happens if you drive twice the fan out? So let's say we have an inverter driving one inverter versus an inverter driving 2 inverters. we want to just measure the delay of this first inverter. What happens when you do that? Well, what is R of the inverter? It's the same in both cases. Yeah, it's the same inverter. What happens to C? Well, C is double. So we have two gates. They both have the same gate capacitance, same overlap, that stuff we talked about at the beginning. It's double. Delay is going to be double. Right? You just look at that and say, oh, that's double the delay. What happens if I use a 2x gate? So what I mean by 2x is that the width, so in this case, I have this, where this is a 1x gate. And then this one here, I have this, and this is a 2x gate. And so in each of these, the transistor widths, so if I draw the inverter, this W goes to 2W, and this W goes to 2W. Whatever it is. So this is WP, this is WN, this is twice WP and twice WN. Well, what happens in this case? If I double the width, what happens to the resistance? Half. It goes in half. What happens here in terms of the capacitance of this fan out? Well, that didn't change. I'm only changing the size of this one. So in that case, we have twice the speed. So this is the drive strength of the gate. And again, this is kind of written as 1x, because 1x is like, this width is usually the smallest NMOS width, and then this one is going to depend on the beta ratio. So we have balanced rise and fall. So that might be 2 or 3 times that W. But then we scale both of them up. So this is still 2 or 3 times this one. Question?
Will EDA tools take into account the size of the fan out and like warn you if
So
those are gonna be wrong?
will EDA tools take this into account? They try to. Usually when you, like an open road, there's a command called repair timing. This is basically what it does. It goes through and says, oh, this path is slow. Oh, I've got a gate with a high fan out. Let me make it a bigger gate. But there's side effects. Now, what if I did this and I made this one twice as big? Well, let me kind of draw it in a different color. What if I had some giant XOR gate driving this? And I still have this giant XOR gate driving this. Well, what happens to the capacitance here is it goes up when I get over here. If I increase the size of those, I'm actually going to increase the output capacitance of this gate. I'm going to then make this gate slower. So just because I made this gate faster doesn't mean that I make the overall path faster. And so it ends up being a complex optimization because you have all these paths interacting. If I increase the size, I improve my delay, but I slow everyone else behind me down. And it's an optimization problem. So then I may want to make this bigger. But then what happens to what drives this? This may have a really big resistance because it's a complex gate. Yeah, the tools try to do that. Yeah.
And when you're doing this on like actual like layout, would it be like exactly 2x, or would it be like depending on the configuration of how things are placed together?
That's a good question. So is this actually 2x, or frequently this 1x will often be some smallest value. Let's see, how much do I want to say right now? I'm going to reserve some of it for the next lecture, where the widths of the transistors in here, this could be like 200 nanometers. And this might be 600 nanometers. And when you double them, this will be 400 nanometers, and this will be, what did I say? 200 and 600. This will be 1200 nanometers. So they might be on kind of multiples of those sizes frequently. And so that's why this is kind of a ratio of this is the smallest one, and you know that the 2x is twice the smallest one. But this is not necessarily an absolute dimension, right? Because the p and the n sizes are actually some other number. But all libraries use that convention of the smallest one is a 1, the 2x is twice as big as the smallest one. and so on. So what are the pros, cons of Elmore delay? Well, the cons, we assume that the input of that switch is a step function. When the switch turns on, that's time 0, and it's a perfect square. In other words, it doesn't account for the input slew. Right? If you have an input to a gate, it's not a perfect step, and so we don't model that in this 0.69 RC. So even though we can kind of predict the output slew, the question, the natural log of 0.9 minus natural log of 0.1, the whole model is ignoring the input slew. So that's another reason it's not good. It assumes this resistor model, which is the average resistance of a transistor over the different operating regions. It ignores short circuit current. That's that brief time when both transistors could be on when the input voltage is somewhere in the middle. That can eat into the delay. And then the output capacitance computation is a little complicated. It depends on the wires and the fan out. A lot of tools will use another term called the effective capacitance, because I'll talk about this when I talk about interconnect, but things that are far away from you in terms of an RC tree actually affect your delay more. Think about it like a wave pipeline, where if a wave starts, the wave isn't seeing the water all the way at the end of the pipeline. It's just seeing the water right at the start. And so when you're driving something, you only see kind of a capacitance that's nearby the driver, not the capacitance that's way far away from it. And we'll talk about that with interconnect models later. But the good thing is it's simple and intuitive. It's fast. It's just all linear equations. Once we get rid of that exponential and we just use 0.69 RC, it's linear. And it has, another important thing is it has good fidelity, but not accuracy. What do I mean by fidelity versus accuracy? Accuracy means, if I run the simulation and the delay is, the equations give me 25 picoseconds, and I run SPICE, it's like 24.9997. That's very accurate. Now, it's not accurate. It'll be far from the result you get in SPICE. Now, what it is, though, is if I have a solution and say this inverter driving a fan out, and then I double the size of the fan out, that difference is going to be 2x. This will predict that the difference is 2x. So the actual absolute delay is horrible, but it knows that the one is 2x slower than the other. So it has good fidelity of saying which one is better than the other when you use the same model. So when you want to make trade-offs, it's good for that. This versus that, both with Elmore delay, it's good. That's why the EDA tools try to do this stuff. A lot of them still use Elmore delay for their optimization. And then they check with better models later. So they'll use this to start and then check with other more sophisticated stuff that's slower to compute. Not quite SPICE, but still slow to compute. So that's the other advantage of this. Okay, as I said, I'm going to actually keep this demo till next lecture. But we're going to release homework 3 end of this week. You still have homework 2, but I'm going to put out homework 3. And then that's the last homework before your midterm, by the way. The midterm's in 3 weeks. We have 2 midterms. So the homework 3 is going to be the last one on the midterm. And then, and so I'm going to put that out there just so people can get a head start and have plenty of time. I know someone's going to write in your reviews or the feedback, you gave us multiple homeworks at a time. I'm doing that for your advantage so that you aren't packed down into a week and you can manage your time. So, don't misinterpret what I'm saying. That I've also done it in the past where I give the next homework after a midterm so people can get started later. But I won't release homework 4 until after the midterm. Then people always yell at me because then some people think it's on the midterm and I'm like, no, it's not. Yeah.
Do you do study guides at all or something like that?
Study guides, no. Lecture material and homework. The homework is the study guide. The tutorials are a good study guide. Yeah. I gave you a lot of homework problems. So homework 2 and 3 are much bigger than homework 1. Not much bigger, but they're more involved, more examples of problems. Homework 2 is fairly small. Homework 3 gets bigger. But based on that, you can also come up with other problems that are similar. So, no question? Okay. So I'm going to reserve this till next time. Now, actually, let's take 5 minutes. Yeah, 5 minutes. So let's get back at 2:40.
Consider vocabulary, like problem. Any updates on the wait list?
I did at the beginning of class.
So if we're having trouble with downloading and
Okay, let's get started again. So we want to basically go from kind of this RC model and talk a little bit more about how this affects gate delays and so on. So we showed this at the very beginning. You know, if you have an inverter, in this case, let's assume that there's the beta ratio is 2. Whenever I give you a problem, I'll tell you what the beta ratio is, right? I'll say it's 2 or it's 3 or usually some integer value just for convenience. But it can change because it changes depending on the process technology. Now, what happens if, for example, we size this from 2 to 4? Well, we know that the resistance is going to go down, but based on what we've talked about, when that resistance goes down, what happens with delay? It goes down. It'll half, right? Half the resistance, half the delay. So what would we expect from this curve? If this curve here is other one. We want the low to high, so going through the PMOS. This is with a size 2. What happens when we have size 4? Well, we can roughly do what we did before and say, okay, if this is, can't really do it super easily on this scale, but like if this delay here was 4, what would the delay be when I did double? Well, it kind of goes off the bottom here, but it'd be 2 down here. So it'd basically shift this curve something like this, way off the scale, right? And then that would also shift this kind of point where things are equal to something like this. And so that kind of affects the overall the equal point where they switch, and it also affects this kind of average propagation delay. So this is the average of the rise and fall. Before I said it could be maximum or average, but this is the actual average. And so it would change this value as well and change the behavior of the circuit. So I just want to kind of point that out, that this is kind of visualizing sizes, right? Now, what happens when we have different logic functions? So if we have an inverter can be thought of as a one-input NAND gate, right? Kind of. It has one input, it's inverting. You take the AND of 1, it's just the same thing. So you have an output. If we have a NAND 2, we have 2 inputs. You get the series connection in the pull down, a parallel connection in the pull up, or you can have a 3-input NAND, ABC. 3 transistors in series in the pull down, 3 transistors in parallel in the pull up. When you have more transistors in series, you end up having more delay. So if we just assume that this is R, what is the equivalent resistance here? It's 2R. How fast do you think this NAND gate is going to be compared to an inverter? Twice as slow, right? It's actually a little bit worse than twice as slow, though. Why a little bit worse? Yeah, the capacitance is a little higher. Because where is the capacitance? Well, remember, you have a capacitor here. You have a capacitor here. You also have a capacitor in here between these 2 transistors. There's technically a capacitor on this transistor as well. So you have more of those. Where over here, you just had a capacitor basically here. For the P and the N. Actually, let me just draw them both to be clear. Then you can have a capacitor here for the PMOS device. Right, so suddenly you went from just kind of this capacitance of this drain to this and this drain, which affect the output. And then the capacitors of these drains and this drain, so 3 of them, plus the one between these two, those all kind of affect the delay a little bit more. So your R is doubled, and now your C is, if you just do it by the number of transistors, that's also roughly doubled inside the gate. Now, I want to point out, though, that usually this is going to be driving some external capacitor C load. Well, if C load is giant, these little red capacitors don't matter that much. So you're going to be dominated by the resistance. If C load is small, then they might have an effect. But it depends. If this is a fan out of 8 gate, C load is going to dominate. If it's a fan out of 1 to a tiny inverter, then the internal capacitances could dominate. Then over here, now we have 3R. So that's 3 times as slow. Plus I have 3 capacitors on the source drain pull up. I have 2 internal capacitances between the AB and the BC transistors. And so I have quite a bit more capacitance internally. So in general, more transistors in series mean slower delay. Now, what's happening to the pull-up delay, though? So in this case, I have a single pull-up in the inverter. Now, what happens over in here? I have these 2, right? What did I say before? Well, what's the worst case of that delay? One of those is on. So let's say A is on. Well, that means this. What would this resistance if just A is on? Well, in that case, it'd be just R. Whatever, let me call it R here for the, oops. Let's call the, I hate when I do that. It's just R of the PMOS, so this would just be R if only A is on, or it'd be R if only B PMOS is on. If both of them are on, it's going to be the sum of the inverses, the inverse of the sum of the inverses, right? But that's the faster case. The point being, the NAND gate doesn't really get slower except in the pull-up except for these internal capacitances, which again can be small compared to the C load. So not much of a difference. And then if we have over here with the 3 case, this is still roughly R in the worst case. So again, the NAND gate pull-up is still roughly the same as an inverter, a little bit because of the capacitances, but not a huge difference. What about a NOR gate, though? A NOR gate can be thought of as a multi-input inverter as well, right? Or an inverter can be a one-input NOR gate. Same idea, things are swapped. Now we have, if this is R, then this is going to be 2R, and this is going to be 3R. But in the pull-down case, if this is R, the worst case here is still going to be R, and the worst case here is still going to be R. So that's not much slower than an inverter, except for those internal capacitances a little bit. So what does this tell you then? Well, first of all, they both scale poorly with large numbers of inputs. You're going to seldom see more than like a 3 or 4 input CMOS gate in any library. Once they get that big, they become really slow and they don't get used. The other thing is, if we start looking at this, how much transistor width do we have to do to have equal rise fall? So here, the NMOS are what are getting slower. Here, the PMOS are what are getting slower. Now remember, PMOS are 3x worse than NMOS usually, 2 to 3x. Having 3 parallel PMOS is much worse than 3 parallel NMOS. Or 3 series PMOS is much worse than 3 series NMOS. So you want to avoid high input NOR gates like the plague. They're awful. Either they're going to be really big by making big, wide transistors, or they're going to be really slow. So why does that happen? Let's look at the equivalent width. So let's just look at the 2 input case for both of them. So again, here we're going to assume what for beta? What are we assuming for beta in this case? Remember, beta is just the WP over WN. It's 2. we're going to maintain the 2 ratio for all the gates. So now, what if I want to make a NAND gate such that it actually has the same delay as this inverter? I don't want it to be any slower. Well, what can I do? Well, if I have 2 series transistors in NMOS, if they were each size 1, how much resistance was it? It was 2R. What if I make each of those half the resistance? So I have now double the width, double the width. So now this is, if this is R over here, now I have R over 2 here because of that size 2, and R over 2 here because of that size 2. So what is the total resistance here? R. I doubled the width. Now it has the same pull-down resistance as the inverter. What do I do for the pull-ups? Now remember, worst case, the pull-ups, one of them could be on. So if I had, here I had a size 2 because of the beta ratio, right? Their PMOS suck. I want to make it wider so it's the same as the NMOS. Now I have 2 in parallel. You know, if we were to say, oh, this one's off, well, then the pull-up through this one is 2, which is the same as the inverter. What if this one's off? Well, the pull-up through this one is 2. That's the same as the inverter. I'm good to go. I can just keep those the same size as the inverter. Well, let's look over at this other case here. So here, let's call this, let's call the PMOS resistance R here. Now here, actually, let's do it all in terms of the red R. What is the resistance of this PMOS? Here, it's going to be R over 2. Why is it R over 2? Actually, no, let me not do that. I'm trying to figure out the best way to approach this. Now, in this case, this has a resistance of R for the PMOS. And here, what is this resistance of the PMOS in this gate over here? Well, this is going to be R over 2 times 2, which is 4, because 2 of them is going to be from this, and then 2 of them is actually going to be because I have these 2 in series. And so the resistance of this is going to be R over 2 times 2. And then if I sum these together, what's the resistance? It's going to be R over 2. That's the same as this, which I actually need to write. This is where I'm differing between the P and the N. Bad explanation. This red resistance is equal to half of the blue resistance because of the beta ratio. So I kind of jacked up this explanation. I size this up double so that these end up having the same resistance. But then to keep this parallel series connection, I need to double the size of these from 2 to size 4. So this then becomes actually not R over 2 by 2. It just becomes R over 2 here. Okay? And this is the PMOS resistance, R, the blue resistance. And then if I combine those end up having the resistance R in this case, which is the same as the original PMOS pull-up. Now this resistance here, blue R, is the same as this red resistance because I made it twice as wide. So this one's half, this difference is 2 because I scaled up the size of that thing. Actually, no, that's a bad explanation. It's actually the same resistance because that's a 2x PMOS. But you get the point, is the important thing to look at is the sizing of those transistors. So in this NMOS, I had to get the same resistance as the pull down here, I had to have 2x transistors. But here I had to have 4x transistors. So half of them are double because they're PMOS, and then they're double again because they're in series. And so that compounds, that multiplies, and I end up getting huge transistors. But the NMOS are actually okay, because here I have a size 1, and for the NMOS over here, I could have, one of them could be on at a given time. And so to have the same delay as the inverter, I can just keep it size 1. Same thing over here, I can just keep it size 1. I don't have to size those up. But if we look at the total transistor size used, what's that look like? So let's say, let me put it in red. What is the total transistor size of this inverter? Let's call it 3. Oops. Right? So it's 2 PMOS widths plus 1 NMOS width. What is the total transistor area of the NAND gate? It's 2 plus 2 plus 2 plus 2. It's 4 times 2. It's 8. That's kind of the total transistor width needed to make the gate. What is the transistor area for the NOR gate? It's 4 plus 4 plus 1 plus 1, 10. So all these have the same delay. But if I implement a NAND gate, it's going to be 20% faster than a NOR gate. Ballpark, 20%. That's a big percentage, right? Or you can think of a NOR gate as 25% slower than a NAND gate. Yeah?
Why is the middle one 8 when not all the resistors are in series?
So this is just the total area. When I do the layout, I need 4 transistors, all size 2, all width 2. So that's the sum of all the transistor widths. So it's not which ones are turned on, but it's which ones are actually in the gate of that size. You're right that I may only use, 2 of these transistors here or 1 of the transistors there, and that is what determines the delay. This is effectively, it's a poor man's way of saying what is the area of the gate. And I'm kind of ignoring all the connections between the things and the length and so on. But the total width of it is roughly the area. Or the other way of saying it is it's the sum of the W of all the transistors. Yeah.
Do you have like a more complicated pull-up or pull-down network?
Yes.
Or you think that-
Yes, I do. Well, first let's talk about these. Here's the sizes of a NOR 3 and a NAND 3. So what do these look like? Well, notice that these only had to go up to 3x transistors because I have 3 in parallel. But this still has a resistance of R. These didn't have to go up at all. Now, these, instead of being 4, these had to go up to size 6. So what is the total area of this? Well, this is 9 plus 6. This is 15. What is the area of this? 6, 12, 18, 21. Now the difference is getting big in terms of the total area needed to make those gates. They still have the same delay roughly as the inverter, but it gets expensive. Now, actually, I don't have an example right now, but the way you can think about these delays is through the, I have examples when I talk about gate sizing and transistor sizing coming up. Is it in this lecture or not? It's not in this lecture. But you can think about it as if I were to have say a parallel and series combination like a resistive network, you want to make it so that every path through that resistive network has the worst case delay. We want to minimize the worst case path through that resistive network. So if you have parallel devices, you assume only the most resistive one is on. And if you have series ones, you have to add them up.
So like you balance all of the worst case.
Yeah, you balance all of them basically because you want to make things as small as possible so you don't over-design any transistors because that's wasted area. But you want to make them fast enough that they don't limit your delay. And there can be more than one solution to a problem sometimes, but most cases there's not. Yeah.
Is this discrepancy the reason that we have NAND flash everywhere now and nobody uses NOR flash anymore?
Kind of. So the question for the microphone is this why we have NAND flash instead of NOR flash? One of them, yes. The other reason is it's very easy to make these series connections. Now remember, how is this connection? That's a good out of context question, but there's actually another important thing we just learned that determines why they do that. How is this connection made in this NAND gate? When you lay it out, how do you connect this transistor to this transistor? No, you do it through the diffusion, remember? If we draw it like, where'd my thing go? Let's say we have the poly gate. Let me draw it in the right color. Where'd my color palette go? I don't know where my color palette went. Well, I'm sorry, my color palette's gone. But if I drew the two polys and I want to connect these transistors, I can connect them just by this shared diffusion region. So if I want to make a bunch of parallel resistors or parallel transistors, how do I do that? Well, I just put a bunch of polys like this, and I draw diffusion like this. These are all series connected, right?
Wait, that's series connected? How would parallel?
You can't do that with parallel. So that's why NAND flash, if you look at layout of NAND flash, the memory storage devices end up being a bunch of these in series in this long string, and then you can turn on one of them and read it out in a certain way.
So on K layout, it would only show stuff in series, not parallel?
No. What I'm saying is this diffusion connection is only for series connections. Not quite true. If I have something like this, let's say I had this on an earlier slide, and then I have a contact, and then this go up to, say, the supply rail. That's actually a parallel connection. Because in that case, you have two PMOS devices, both connected to the supply, and then they branch out, and then they get connected to other stuff. But you're still connecting those two transistors through the diffusion region, the green, and then you're also going up a contact and connecting it to the supply. So in that case, it can be used for parallel, but you can't easily do more than one connection. I'll talk about it when I talk about cell libraries a bit, maybe. So that's why they use it for NAND flash. It's very dense. The layout's super tight. Now, let's see, I'm not sure what's going on here with my view. I have no idea where my palette went. Now, I already kind of alluded to this, but remember when I was drawing them, I said there's capacitors between everything. We talked about this at the start. This is kind of the secondary component of these capacitances. If we look at an inverter driving a fan-out, we have a number of capacitances. So left is the inverter, and this fans out to one inverter. What are all those capacitances? Well, here we have kind of these are the, basically these capacitances, I don't want to phrase it. So we have the gate capacitance component here. It's the gate to body. We have these kind of, these are called the drain and bulk capacitances. But they're actually not necessarily to ground like I've been drawing them. They're technically to that fourth terminal of the transistor. So remember, these transistors are either on the substrate or in a well. Remember I drew that diagram before? And so